please.
Yes. Thank you. My name is Eike Lorenz. I'm from the Institute of Integrated Production in Hanover. We are a non-profit organization and a affiliated institute to the Leibniz University of Hanover. And we conduct research in multiple areas. One is my project, or the project I'm assigned to, which has the goal of determining the rotation angle and torque contactless and ideally optically. And thank you to the Austrian Institute of Technology for the opportunity to talk about this today. So starting with a little bit of background and to provide a bit of motivation why this would be important, why do we want to measure rotational speed and torque. Anywhere where we use a rotating shaft to transmit power, we need these two values to provide control, to provide predictive maintenance or values for the predictive maintenance or condition monitoring. This might be the two logos on the left describe the generators in wind turbines or hydro power plants, but also in the maritime sector, the ship's propeller has a shaft, the fan shaft in the jet engine, or in a car we have the cardan shaft which transmits power. And all of these shafts need some kind of measurement to know the torque and the rotational speed. Oops. Sorry. Now, so this is nothing new, and why do we invest time in researching new technologies here? We already have sensors for both of these measurements. On the left you can see a conventional rotary encoder to measure the rotational speed, and stain gauges usually provide the torque measurement. So why do we need something contactless and something new? These two sensors have two disadvantages. The first big one is they're not contactless. So you need to attach them somehow to the shaft, which is cumbersome. You need a lot of labor to do so, and in case of the stain gauges, it's also very complicated to do it very precisely. So they have the first disadvantage, it's not contactless. You have to attach them, and the second disadvantage is you have two sensors for both of your measurements. So it would be better to have an integrated measurement and a contactless. What kind of contactless methods could we use? What physical properties could we use to measure these two variables? Rotational speed can be measured contactlessly in different kinds of methods, and torque as well, but they have one in common, which is the optical property. So the optical measurement provides the possibility to have an integrated method which both measures rotational speed and torque. This is something at the Institute what we are now researching, or where we are now working on for the past 10 years already. Starting with Integrat in 2014, it was the first research project where we laser engraved barcode markings on a chrome or normal steel shaft, and this provided us the rotational angle at two positions, and if there would be a moment attached to this shaft, we were able to measure this. And 5 years later, the next research project was called MiniVip. It downsized the whole sensor setup quite a bit and also increased the stability against vibration. And now, we still were reliant on these laser gravings, which were also very difficult to engrave precisely on this curvature of the shaft. So we want to go away from this barcode style engraving, and we only want to use the naturally occurring features of the steel surface of the shaft. So here you can see the surface of the, or how the surface looks from a steel shaft like that, and already on the first glance you can see a lot of features that might be that we might be able to exploit to determine the rotational angle. And this modification-free approach I want to show you on this scheme here. In the center you can see the torsion shaft, which transmits the power. And so if now power is transmitted via this shaft and you have a torque applied there, you have a angle, the torsion angle. This torsion angle increases with the length of the shaft. And if we measure now the difference of this angle from one point to the another point with a fixed length between that, so phi 1 and phi 2, we can then compute back to the moment. How do we want to do this? First, for each cut out section here, we want to create a panoramic surface image. This is seen here on the bottom. And so we map all of these features that occur on the shaft surface and map them to a single angular value. And then when new images come from each camera, we can match those to the panoramic image and find out what the corresponding rotational angle is. And then if we have the two rotational angles, we can then again determine the phase difference, and we know the moment. We divided this project in 3 sub-goals. First, we create this panoramic images of the fan surface. Next, we want to investigate feature-based matching algorithms to match the occurring features, the occurring frames to the panoramic image. And lastly, evaluate that under different conditions. Here, I hope this works, you can see what the camera sees. We use a 12-time magnification, and you can see already there are a lot of features or characteristics we might be able to exploit for this operation. And I hope another thing is now visible, and this is the unroundness of our used. Now you can see that it gets blurry, and this is caused because we have this high magnification, and we're very sensitive to any distance changes between the surface and the optics. And another real-world problem that you can see now are these dark spots. This is pollution, either on the optics or even worse on the surface. So then why do we need this high magnification? The shaft is round, and we want to mitigate or minimize any effects by the curvatures or any projection errors as much as possible, and have a flat surface, or the surface should be as flat as possible that we use for our operation. I'm just going to let this play out. After that, we go back to 360 degrees and it gets sharp again. So the first step was creating these 360 panoramic images, and for this we use consecutive images. So image 2 follows image 1, or image 1 is precedes image 2, and they both have an overlapping part. This is shown here in this yellow part. It shows the same part of the surface image, of the shaft surface. The red part is only visible in image 1, and the green part is only visible in image 2. And from these consecutive images, step by step, we create this 360 degree panoramic image. Down here you can see the section made up only by two images. If now a third image would come up, it would be then again matched to the panoramic section. How is this done? This is right now done by cross-correlating these images. Some first insights. Here you can see the apart from the panoramic image, if there's a tilt in the camera. So as you can see, the resulting panorama is very skewed, and you get a lot of black pixels that are very useless and only take up valuable information, computational power. For the accuracy, this is a bit complicated. This graph, what I tried to show here, on the x-axis you can see the images, 720 images, and on the y-axis you can see the offset between each image. And between each image we rotated the shaft by 0.5 degrees. So we would expect that the offset is steady at 0.5 degrees, but it's not. And we're wondering why was this the case. We thought maybe it's because of the unaligned camera, which was tilted, but it turns out it was the transmission by the worm screw. So the worm screw turns 48 times to turn the fan shaft, or to turn the shaft one time. And this is exactly what we can see here. So our method was actually accurate. It was just a mistake on our end that we thought it was something else. And it proved as an accuracy test at the end. So what we can see here is a first test that, or first proof of concept that we have an accuracy of less than 0.02 degrees. Now we want to go back away from this. So this was the first sub-goal, and we want to move to the second sub-goal, which was the feature-based approach. Feature-based approach we can divide into these four groups: detection, description, matching, and outlier filtering. And for this, again, I have these two images that we already know already. So between image 1 and image 2, the shaft is rotated by 0.5 degrees. And we want to find correspondences between this. We use the scale invariant feature transform algorithm to find possible key points and describe them. And all these blue dots are possible key points that might be exploitable for the image matching. Now we don't want to use every, so we can save some computational power. So we only use the 50 best. These are then matched by a very brute force similar method, the k nearest neighbor method. And as you can see already, the 50 best matches appear to be quite reliable. How can we see if those are truly positives and not false positives? The more they are parallel to the direction of the shaft rotation, the vector down here, the more confident we can be in these matches. So just for an example, I can show you a false positive. It looks like this. So it's angled towards the rotation vector, and also you can, by just the first glance you can see this is obviously not the same point. This is our future, the things we want to investigate in the future, this feature-based image matching, to make our method more quick and more reliable. And this also already concludes my presentation. Myself and my colleague Niels Jansson over there, we both work on this project. The project homepage you can visit if you like, and we're happy to get in touch with the one or the another. Yes, thank you.